So they've given us this function, and at positive 2, we have a problem. At positive 2, we have a 0 in a denominator, which is a problem. On top of that, we cannot cancel it out. So hopefully we remember that this creates this little dotted line called an asymptote, right? This little guy right here. Now here's the problem. This is one of my 3 things that say overall limits do not exist, okay? So when we start talking about infinite limits, understand that once again, this is a concept. Infinity is always a concept, right? If I said, what is the number infinity? It's not a number, it's a concept of numbers. It is a continuation forever of a number set, okay? So when you talk about an infinite limit, you are not talking about a real number limit. You would still say the real number limit does not exist. But if I was asking for the limit, you could give me an infinity as an indicator of what happens to the graph as you move towards that number. And that's what an infinite limit is. You are strictly telling me, I do not have a real number to give you, but I can tell you what's happening to the graph as x move towards that value. And so you can see right here that as x moves towards 2 from the left-hand side, we have this strong turn towards negative infinity. And as x moves towards positive 2 from the right side, it shoots up to positive infinity. These are examples of infinite limits, and they work the same as an overall limit. For this one, I would say it does not have an overall infinite limit at all. This only has a left and a right-hand limit. The left-hand limit would be negative infinity. And by saying negative infinity, and it actually says that, you're actually saying, in fact, it doesn't have an overall limit. It increases without bound. There is no boundary on this whatsoever. Whereas the word limit actually indicates boundary, right? So if you have a speed limit, that indicates that is the boundary at which you should stop going accelerating, right? If you have any type of limit, a spending limit from your parents, right? Then that is a boundary that they have set that you don't go past. By saying negative infinity or positive infinity, you are actually saying there is no boundary, there is no limit, but I am going to tell you what happens to the graph. So you'll see something like this, and they will actually say, what is the limit as x approaches 2 from the left-hand side? And you would actually say, oh, well, that is negative infinity, right? Even though technically it's unbounded and there is no limit. You are simply answering the question, what is happening as x approaches 2 from the left-hand side? All right, does that make sense? Let f be a function that's defined at every real number in some open interval containing c, except possibly at c itself. The limit as x approaches c of f of x equals infinity. It means that for each m greater than 0, there is a delta greater than 0, such that f of x greater than m whenever 0 is less than x minus c, which is less than delta. And then they give the same thing for negative infinity. What does this mean? Well, this means that if I am going towards positive infinity, then every time I move that direction, my y is moving up. And it keeps going forever. And conversely, negative infinity, as my x moves towards it, my y value is moving down infinitely, pretty much. So that's what they mean by infinite limits, all right? So let's first look at infinite limits by graphs, page 81. Looking at a graph's very simple. Infinite limits are, visually, I don't even have to really teach this. If I give you a graph and I say, hey, if I were to look at these figures, what are the limits of each figure? You can see that the first one I would have to only do left and right hand limits because I couldn't just say overall what's happening across the board. So as I'm approaching 1 from the left, negative infinity. 1 from the right, positive infinity. That's clear. For the second graph, B, well, as I'm approaching 1, it doesn't matter. I don't even have to put left and right. It's going to be positive infinity, right? The next one, positive and negative infinity. And the last one, negative infinity. So you can see where you could list it as an overall, right? Left and right could be the same thing, or they can go different directions, right? But visually, when you have a graph, it doesn't even take, it's intuitive, okay? When it's not intuitive is when you start having just the function, all right? So let's look at vertical asymptotes. First, this is usually what it's going to ask for. Remember, removable creates a hole. Non-removable creates a vertical asymptote. When you have a hole, your limit is going to be a real number, okay? So if you have a hole in a graph, you are going to be approaching that hole on both sides. And that hole is your limit, technically. But when you have an asymptote, a non-removable, you are going to have an infinite. You are not going to have a real number limit. You are going to have an infinite and an asymptote. Because the very definition of that says you move infinitely close to it and never touch it, which means you have to move infinitely in one direction. So if it is removable, you're going to have a real number limit. If it is non-removable, you're going to have an infinite limit. And that's how you're going to visually be able to see it without a picture of a graph. All right? So definition is if f of x approaches infinity or negative infinity as it approaches that number from the left or the right, then x equals c is a vertical asymptote. So now all of a sudden we have defined vertical asymptote using limits. Okay? So we know the whole non-removable term. Now we're going to say, hey, if you're approaching infinity when you move towards this, then you have a vertical asymptote. So they've kind of flipped it. The theorem, let f and g be continuous on the open interval. If f of c does not equal 0 and g of c equals 0, you'll notice f is the numerator, g is the denominator, and there exists an open interval containing c such that g of x doesn't equal 0 for all of x that does not equal c in the interval, then the graph of the function is given by this, and it has a vertical asymptote. What are all those words saying? They're saying if you have a rational function, a numerator and a denominator, and the denominator becomes 0 at some point c, and you can't take it out, non-removable, you have a vertical asymptote, okay? That's what they're telling you there, all right? You have a rational function, numerator, denominator, 0 on the bottom that can't be simplified out, vertical asymptote exists, all right? So let's look at these. Determine all of the vertical asymptotes first. And you see the pictures below. So this first guy, what's my problem here? Vertical asymptote happens at x equals -1, right? Just -1. Just -1. If that 2 had been inside the parentheses, it would have been -1/2. All right? -1. You can see from the graph, we have this guy right here. All right, look at the next one. Is the top, is that factorable? X squared plus 1. No, if it had been cubed, it would be, but it's not. The bottom is, however. How do we factor the bottom? Yeah, x plus 1, x minus 1, which means neither one of those are removable. I have 2 vertical asymptotes. I have a vertical asymptote at -1, and I have a vertical at +1. And you can see from the graph that's what happens, all right? Last one, cotangent, all right? Cotangent is x over y, correct? So anywhere y is 0, you will have a vertical asymptote, all right? Which is why this is a repetitive function. This is a cyclic function. It cycles, right? And it cycles with those asymptotes. And those asymptotes are every place that x is 0. That y is 0. So at your 0, at your pi, at your 2 pi, at your 3 pi, 4 pi, 5 pi, like everywhere that y equals 0 for all of infinity, you're going to have an asymptote for cotangent. And then the opposite is true for tangent. So for tangent, everywhere x is 0, you're going to have an asymptote, okay? So let's look at this first one here on example 4. Can I factor the top? Yes. Factors of 8 that subtract to give me +2. Yeah, so I have a +4 and a -2, right? So 4 times 2 is -8. 4 minus 2 is +2. On the bottom, that's a special case, right? Now, if it asks for discontinuities, I would have 2, all right? Right? I would have a hole at 2 and an asymptote at -2. They are only asking for vertical asymptotes, okay? So my only answer here is going to be what? -2, okay? And then you can see from the graph what happens here, all right? So you can see from the graph, -2, asymptote, +2 is removable. So this is where, if you had a limit, if it said the limit as we approach -2, we'd have a left and right hand infinity, okay? But if it said +2, we'd have a real number. Do you see the difference? Removable is going to be a real number limit. It's just a whole. Non-removable is going to be an infinite limit. They want me to figure out what the limits are. So my first job then is to factor. I'm going to look at the first one. All right. These are the same exact ones. What's the difference? Limit as x approaches 1. What's the difference on the bottom? Left and right. Okay. So we're going to factor it, and then we're just going to figure it out. So we have, take out an x on top. We have x minus 3, right? Is that 1 removable? No. So I know I'm going to have an asymptote, okay? So now I'm going to figure out what's going on. Once you figure out you have a vertical asymptote, you know your limit is going to be an infinite limit. You just have to figure out positive or negative, all right? So let's figure out positive and negative. We're going to look at from the left-hand side first. All right? From the left-hand side, meaning on the number line, I am just to the left of positive 1. Okay? So let's talk about what happens. Just to the left of positive 1, just a teeny bit smaller than positive 1, like 0.9, okay? So would it make this one right here positive or negative? Just barely left of positive 1. Positive, okay? So that guy's going to be positive, all right? Times just a little bit smaller than positive 1. Positive or negative? Negative. Just a little bit smaller than positive 1. Positive or negative? What are my rules of multiplication and division? Is that answer going to be positive or negative? Yeah, I have 2 negatives, right? Any even number of negatives. So this guy is going to be positive infinity. Does everybody see what I did there? All right. We're going to take the same exact thing and we are going to do it with just a little bit larger than 1. I'll change the color. So the limit as x approaches 1 from the positive side. All right. So let's do this all again. Just a little bit bigger than positive 1. X is going to be what? Positive or negative? There we go. Just a little bit bigger than positive 1.
Or negative.
Negative, right? 1.1 minus 3. We're going to get a negative number there. Just a little bit bigger than positive 1. Positive, right? I have 1 negative. It's a negative infinity. All right? So that's all you're doing with these. You are legitimately first, non-removable. I know it's going to be an infinite limit. Now let's just figure out which way. Using my logic skills from like algebra 1. Okay? Yeah, so I would factor, right? Non-removable is going to be infinite. All right? So non-removable is going to be an infinity or negative infinity. All right? And then go from the left and right. So from the left is a little bit smaller. So determine positive and negative. All right? And then from the right, which looks like a plus sign, a little bit larger, determine positive and negative. And then you're really just using your rules of multiplication and division, right? So an odd number of negatives is going to be negative infinity. An even number of negatives is going to be positive infinity. All right? So properties of limits, really, the same holds true for infinite limits. You do have to think about when you're talking about infinity. So if something is moving towards infinity and then you have like a plus 2, it's still going to be moving towards, or even minus 2. So let's say you end up with, okay, this section of it is moving to negative infinity, but then I have this plus 2. Well, think of it this way. We have, someone like Bill Gates, we'll use him, right? Is he going to miss $100 more or less than you would? Probably less, right? I mean, you know what I mean? So we have someone with $1 million, way more than $1 million, and they lose $10, right? It's not affecting them. You have someone with $20 and they lose $10. We have a problem, right? And so this is how infinity works. You still have the same concepts. You have like, okay, positive infinity plus 2. I'm still moving towards positive infinity. Negative infinity plus 2. Even though the limit of this piece is 2, this negative infinity is not affected by that plus 2 at all. It's still moving towards negative infinity. So your overall limits still work. If you have an infinite limit plus something that has a real number limit, you'll notice, so this function has an infinite limit. This guy has a real number. It did not affect it whether you added or subtracted, right? It did not affect it if you multiplied it. The only way it affects it if you multiply, however, is if that real limit was a negative, right? So if I have an infinite limit plus or minus a real number, it's still going to be whatever infinite limit it was. If I take an infinite limit and multiply it by a negative number, well then my positive, you can flip-flop positive to negative if you're multiplying. Adding and subtracting will not affect it. So if you have one piece of it that moves towards positive infinity and that whole thing is multiplied by -1, then your whole thing's moving towards negative infinity, right? Quotient's the same way. If you have an infinite limit on top, it's not going to affect your quotient at all. Take infinity and divide by 4. Okay, guess what it is? It's infinity. However, if you flip-flop it, your numerator is a number, a real number, 4, and you are dividing by infinity. That is a 0. That's a 0, okay? So you do have to think about your rules, like when we had horizontal asymptote rules. If your exponent's larger on top than on bottom, like those rules, we're going to get into that with infinite limits as well, because it will affect it, okay? If your infinity is on top and it is cubed, and you have something on bottom that's squared, the infinity is going to take over. If you have an infinity on bottom cubed and it just an infinity on top, your infinity on bottom is growing exponentially larger, faster. You're moving towards 0 because you're dividing by a really big number, right? And the same holds true if you have just a whole number on top divided by infinity. You're moving towards 0. Your denominator is getting infinitely larger while your numerator stops, okay? So when you start thinking about infinite limits, you have to say plus or minus, not going to affect it. Multiplication only affects the positive and negative. Division, where is my infinity? So what's going on with the infinities? Is it growing enormous on top? Then it's going to follow the infinity on top. Is it growing enormous on bottom? Then it's probably going to be moving towards 0, okay? Make sense? And you can have an infinity divided by a negative. That's also going to affect your positive, because technically that's multiplication, all right? Everybody understand those? Okay. You're like, sure. All right, so let's look at these infinite limits. Determining limits. Because the limit as x approaches 0 of 1 is 1, all right? So 1's not affected. If I'm approaching 0 here, on the bottom I'm going to have a problem, right? The numerator is not changing, okay? So we're going to decide what's happening. Well, the bottom is squared. So the bottom will always be either positive or negative. What? If you square something, it's always positive. So if we do that rule here, my numerator is always going to be a 1. My denominator is moving towards positive infinity. Okay? So what's going to happen to this guy? Right, so I have 1 plus 1 over is I'm moving infinitely close to 0. Now, here's what you have to think about here, though. What type of infinity am I moving towards? What's happening here?
That's a good question.
That's a good question. So I guess my question is, as I move towards 0, am I talking about whole numbers when I talk about moving towards like an infinity? What's actually happening if I move towards 0? So I have 0 on this side of 0 and on this side of 0. We're not talking about 1. or negative 1, okay? We're talking about fractions, right? Does everybody understand that? So in this case, I'm not really moving towards a whole number infinity. I'm actually moving towards fractions. All right? So I actually have 1 over a fraction. Let's pick a fraction close to 1. 1 over 10. What does that guy actually do? 1 over 10. What is he? 10. Okay. 1 over 100, because that's even closer to 0, right?
It's 100.
So what's happening to a fraction if I reciprocate something moving towards a fraction? You're actually, the whole thing is moving towards infinity. Does that make sense?
Sure.
You see why that's happening? Because I'm reciprocating something that's moving towards a really tiny fraction. Normally a really tiny fraction would be moving towards 0, right? But I'm flipping that really tiny fraction. I'm flipping it upside down, so those numbers are getting huge, okay? Look at this guy right here. Now this is a plus or minus. If I move towards an asymptote here, and I square it, then this guy is going to be fine. We can just plug it in, right? It doesn't matter that it's coming from the left and right. I don't have an asymptote there. No issues. So that means this numerator is just going to be a number. This is just going to be 2, right? For this. So my limit for as x approaches 1, no matter which side it's on, of x squared plus 1, is just 2. I can just plug it in, right? This guy is negative infinity, all right? So now I have a 2 over a negative infinity. Why is this approaching 0? Well, my 2 is not changing. My denominator here is getting infinitely large. Infinitely large. So he's getting to be just like this up here, but not flipped. These huge numbers on bottom, he's moving towards 0. So anytime your numerator stays the same and the bottom is getting larger, in this case, the bottom was getting smaller, right? Because we were moving towards a fraction. This guy is getting larger, then we're moving towards a really tiny number, which eventually moves us towards 0. All right? Look at this last guy. They want 3 cotangent. The limit of a constant is just a constant. So 3 doesn't change. The limit of the cotangent of x is infinity. So basically I multiply 3 times infinity. Okay, it's infinity, right? Had that been negative 3, it would be negative infinity. But this is just positive infinity.
Oh, I got it. Oh, okay. It like literally tells. Okay.
Yes, it's telling you 1
Gosh, I was like,
infinity.
I don't know.
1 plus infinity is just infinity.
Okay.
There's so many like.
I was
Right,
making it
whatever,
way
so
harder
weird.
that I was like confusing myself. I was like, what is happening right now? But
Hang on.
okay, I got that.
Hang on, look.
It,
They start with the answer. So here's what they want.
Okay.
What is this answer? Okay?
It's just 1
The limit of 1 is just 1. The limit of this is positive infinity, right? Because it's going towards 0, and so you're flipping that fraction. All right? So you basically are saying, well, what's the limit of the whole thing? Well, it would be the 1 plus infinity. Well, that's just infinity.
it literally like gives it to you.
Right? Look at this next one.
Like I was overcomplicating it.
This next one, they want this guy right here. That's what they're ultimately asking you, right here. The limit of the first piece is just 2, because you can plug it in. All right? The limit of the second piece is negative infinity. So you have 2 divided by this humongous number. Anytime you have a number on top and a ginormous number on bottom, you're moving towards 0. You're moving towards 0. You have to be. You're taking 2 and you're dividing by 10. Then you're dividing by 100. Then you're dividing by 1,000. Then you're dividing by 10,000. The number is definitely getting smaller, right? So this is going to be 0 because you have a number on top and a huge number on bottom. You're moving towards 0. So they've given you the 2 pieces. They've given you the numerator and the denominator limits. 2 over infinity. Or negative. It doesn't matter that it's negative or positive because you're moving towards 0 there. This last one, they want this overall limit here. They want the limit of 3 cotangent of x, okay? The limit of 3 is just 3. The limit of cotangent of x is infinity. So you end up with 3 times infinity. So your overall limit is just infinity. They're just taking each piece of it. And they're saying if you take this piece and this piece, multiply or divide it, whatever, or add or subtract it. Okay, the first one we added, 1 plus infinity. Well, that's just infinity. Here we divided a whole number by an infinity. 0. Always moves towards 0. Here we multiplied infinity by a number. Still infinity. That's all I did there.